What if, okay, now the next one. What if this is the right-hand side change, which is the B change? The current B, okay, current B, with the lambda, with this parameter, change towards a direction called B prom. And the new right-hand side called beta. That's what we call the beta. So suppose we have an optimal feasible solution to the CB transpose times XB and B XB, B times XB plus N times XN equals to right-hand side B, and XB and XB greater than or equal to 0, XN currently equal to 0, but it could be a positive number only. So we can, we know that. So we know that currently Zj minus Cj equal to Cb transpose times Yj minus Cj. Since currently is optimal, they all has to be non-positive for all the j, all the column. We're going to replace B by beta. Beta equals to B plus a lambda times B prom. B prom is the change vector. So the new basic solution, x hat B equals to B inverse times beta, which is equals to B inverse times B, the original basic solution, plus the lambda times B inverse times B prom, and is equal to lambda times B inverse times the changing of the vector. So equals to the current basic solution plus lambda times the change of the basic solution. However, this has to be non-negative based on the non-negativity assumption. We can have also B inverse times beta, which is the new right-hand side, is also of optimal basic feasible solution if this is maintained, the non-negativity constraint is maintained. And which we can maintain this, and then for all of them, that will be no problem. So look at this. The current XB is non-negative. If the X prom B, any elements are non-negative, then this whole term, so non-negative plus a positive times a non-negative, then will be always non-negative. So for that, if for X prom B, Bi, is greater than or equal to 0, and they have no problem with that current solution. However, if some of the situation is not that ideal, we see what happened. Let's look at example. Minimize negative 3x1 minus 2x2 minus 5x3, and subject to x1 plus x2 plus x3 plus x4 equals to beta 1, okay? 3x1 plus 2x3 plus x5 is equal to beta 2. x1 plus 4x2 plus x6 equals to beta 3. And x1 to x3 are non-negative. So we can see that x3, x4, and x5 and x6 are slack variable. And we're assuming the original, the beta, which is the new right-hand side, equals to the original right-hand side times the lambda times a perturbation vector. This vector will be 100, negative 200, and positive 400. Okay, so the 430, the 460, the 420 are the original right-hand side. So let's see how we put it into a objective function. Look at this right-hand side. I divide it into two column now. So this is the original optimal tableau. I didn't do nothing. And the pink area is the B inverse matrix because x4, 5, and 6 are the slack variables. So this position is always the B inverse matrix exists. This is the current solution, 100, 230, and 220. My basic variable is x2, x3, and x6. All right, so we can see that x2 basic basic column, x3 basic column, and x6 is another basic column. Right hand side also got changed, was b inverse times xb prime. So this will be 300 times lambda. This is 100 times lambda. This will be negative 100 times lambda, and the last one will be 0 based on the calculation. Okay. So let's see how this is going to get calculated. XB hat, which is a new right hand side, new basic solution, equals to the B inverse times beta, and beta equals to that. Has to be greater than or equal to 0. So it's 100 plus 100 lambda, 230 minus 100 lambda, and 20 has to be greater than or equal to 0. So if we want to maintain this to be non-negative, so only this one will matter, okay? Because lambda increase, this x3 actually decrease. So lambda should be between negative 1 to 2.3. And lambda start with a 0, so negative 1 we start with a 0. So basically what we're saying, between 0 to 2.3, and the current right hand side is still feasible. Okay. And look at the changes of objective function z hat. Z hat equals to CB transpose times XB hat. XB hat is a new basic solution. And the CB equals to negative 2, negative 5 is C2, and C3, and C6 is 0. Times the current basic solution equals to negative 1350 plus 300 times lambda. So if the lambda keeps going up, the overall objective function going up as well. So deteriorate my current optimal solution objective function value. If lambda is greater than 2.3, there will be no feasible solution for the primal problem because there's a negative elements on the right hand side. In general, we just perform do simplex method. Oops, sorry. Just give me a second. Okay. So what I have is the horizontal axis is lambda, and the vertical axis is the basic new basic solution, xbi plus lambda times x prime bi. When lambda keep increasing, some of them, the basic solution, some of the basic variable decreases value, some of the basic variable increases their value. But they all started with a positive range because the basic variable originally, they are positive or zero value, greater than 0. So some of them going increase, some of them going decrease, but the only one we will care is for those going decrease. And the minimum one we call the lambda 1 is the first one hit the 0. Because if I keep increasing lambda, and this particular variable go negative. And that's the range. All right. This pretty much conclude the second part of the lecture 7 called parametric analysis, and sometimes we call it parametric programming. Okay. We're going to conclude this lecture from here. Next time we'll talk about lecture 8. Talk about simplex method with the bounded variables.